Y16 phase shift in RLC circuit. So we have driving force, EMF has amplitude, and we consider cosine, sine, or exponential. And the solution of Q will have a phase shift delta. But in general, when we consider circuit, we are more interested in the current. And the reference equation is V equals IR for resistive load is given. The potential difference is proportional to the current, and V and I are in phase. So when we consider current instead of charge, we use a different notation, that is a phi. They are closely related by half a pi. We will see. Here, when we consider mechanical system called the simple harmonic oscillator, we introduce the phase shift delta. In any case, that delta dependence cancels completely because of the first order derivative term. That is the origin of the phase shift. However, if we take the derivative, cosine becomes a sine, and cosine becomes a minus sine, and sine becomes a cosine. In this case, no change, except that we take the derivative, then including omega, we have additional factor of I, and that factor of I is exponential I e to the I half a pi. This one is included in here. So in addition to the phase shift minus delta, that was necessary to find out the correct answer for charge Q, we have a phase shift by plus half a pi after taking the time derivative. So that's the reason why we have these two contributions. We had minus sine omega t style minus delta in here, and this minus is included in here to return to the same function cosine, to return to the same function sine, and it is always the same function exponential. Anyway, this guy, this guy, this guy are universal. Okay, we will treat these sum of these to be phi later. Anyway, if we take another time derivative, second order time derivative, we have minus omega squared. Then phase shift returns to this original form, except that everything has a negative sign. You will find omega dependence of the amplitude appears to be like that. We have done this calculation so many times, so let me just pass sine, cosine, delta dependence like that. Now, we change the variable, because I don't like to write half a pi minus delta so many times. Instead, why don't we write this one as minus phi? This is not an azimuthal angle. This is just a phase constant. When we treat the current, remember phi minus phi, then we are considering current instead of charge Q. When we consider charge Q, minus delta, current I minus phi, remember, don't forget. So we return to the high school. Cosine x minus alpha pi. Cosine is an even function. I can exchange this order by cosine x equals to cosine minus x, even function. And this is sine. And sine is an odd function. Sine minus x is minus sine x. Therefore, we have negative sign. And this is, triangle theta half of pi. And this one must be half of pi minus theta. That's the reason why sine half of pi minus x this is cosine. Cosine half of pi minus x, this is sine. Anyway, what we have found previously can be interpreted as this form. Now, current I is our reference. Half of pi minus delta has been replaced with minus phi, minus phi, minus phi. We consider this, and from this, we find another derivative that is a time derivative of current, and we have integration Q, that is time integral of current. So this is our reference. If you want to find the charge, what you need to do is time integral. If you want to find the time derivative current, then use this. So current is our reference. And the phase shift for the current is minus phi. Remember. These are what we have just studied. Our reference is for the resistor. And if you want to find the potential difference between the two terminals of a capacitor, you do time integral. If you're interested in the potential difference between the two terminals of an inductor, you take the time derivative. So this is our reference. If you take the time derivative, cosine becomes minus omega. In here, sine becomes cosine omega. In here, I omega L. In any case, we have omega L style. If you look at this, it brings in imaginary part with positive sense. What about the capacitor? If we use exponential form, this I omega appears in the denominator. To replace this one, we have I in the numerator, then I need to attach a negative sign. Therefore, in the case of capacitor, its potential, we have negative sign omega C in the imaginary part. This one is imaginary part. And only the resistor, everything has real number. So this is a real part, and capacitor and inductor, they bring in non-vanishing imaginary part with positive sense and negative sense. So it is convenient to find that these are all potential difference between the two terminals of a resistor has the amplitude, current I's amplitude multiplied by R. In here, inductor, as far as amplitude is concerned, amplitude for the current multiplied by omega L. This negative sign represents the phase shift. In the case of capacitor, what we have to do is we have a phase shift by half a pi, and the weighting factor is minus 1 over omega c. So that's the reason why we have, it's a rather simple to define these omega dependent factors that determines the potential difference between the two terminals of each circuit element. Why don't we call this one as XR, XL, and XC? Okay. We find this form repeatedly. And these guys, they have phase difference by half a pi. If we consider cosine, sine, in any case. And if you consider exponential, it is explicit that this XR and this XL minus XC, they construct a complex number. R represent the real part. XL subtracted by XC represents an imaginary part. Okay. And if you have a complex number Z equals A plus BI, then what you're going to do is take the modulus and this one has the absolute value to 1, that is exponential I something, and this is a phase. Okay, in summary, this delta minus delta was for the phase shift for the charge Q. Now we are more interested in the current. The phase shift for the current has additional piece that is half a pi because of the time derivative, and we define this sum to be minus phi. That represents the phase shift for the current instead of charge. Then this phase shift cosine value or sine value, cosine is nothing but the real part ratio relative to this number, absolute value of this number. This is called the impedance. And what we call this XR, omega L, XL, 1 over omega C, this XC, these are called reactances. Resistive reactance, inductive reactance, capacitive reactance. And this is the real part. You know, the complex number was XR plus I, XL minus XC. And absolute value of this complex number is called impedance. Okay. Phase and time derivative. We studied this repeatedly. Whatever sinusoidal function is, whether it is cosine, sine, or exponential, it's a time derivative according to chain rule, omega multiplied by this function. Okay? Double time derivative, omega squared multiplied by this function. This is just the phase shift after the derivative. If you take the triple derivative, usually we don't need that, then we need another half a pi shift, because the green one, red one, blue one, as you take the derivative, it makes a phase shift by half a pi repeatedly. So these are complete set of result, whether you consider cosine, sine, or exponential. Whatever, the result is the same. So phasor is a complex number. This one is very, very useful for the circuit. And in addition, later, when we consider interference of a wave in general, it is so useful. So because whether sine, cosine, or exponential I omega t, whatever case, the phase shift was the same. So it is convenient to consider complex number instead of each real or imaginary part of this complex number. So we have Q, and this is a complex plane. And after all calculation has been done, what you want to do is just to take the real part of this complex number or imaginary part of this complex number as you wish. In any case, take the time derivative. Most general complex number case, time derivative will bring in I omega. So we have a phase shift. This one is half a pi I, phase shift by half a pi, forward. Forward means forward, means counter clockwise. Okay, half a pi. If you take another derivative, half a pi forward. Originally, your answer must be delayed by minus delta due to what? Ri term. This one brings in delta for the charge Q. And the current, half a pi forward, and time derivative of current, half a pi forward, and so on. So the reason why we use XC, XR, XL so frequently is like that. Regardless of specific shape of function, whether cosine, sine, or exponential, it's the structure of the phase structure is just subtraction or addition of half a pi, forward or backward. So we have learned reactances and impedance expressed in terms of XR, XL, and XC that determines the amplitude for the current completely. So if we use phasor, the computation is quite compact. Impedance, they behave like a resistance for the resistive load. Amplitude is completely determined by this reactance multiplied by the amplitude of the current. And this is a sinusoidal effect. Whether you use exponential, cosine, or sine, everything is the same. Let me just explain the exponential I omega t style to the circuit equation. This term represents Ri. Our reference is current I, so current I has an amplitude and sinusoidal factor. Okay, and then we have additional term that is either forward or backward. We use the forward case as a reference. Capacitor is backward by half a pi, but that is use the same shape of function, but pull out this negative sign on it. Okay. Therefore, because it is e to the I omega t, and this one is I times e to the I omega t, this e to the I omega t can be factored out in this form, including the phase for the current. In that case, what we are left as an overall factor is this complex impedance. And from this complex impedance, we can read off the phase for the current. And we can read the impedance, Z, that is the absolute value of this complex number. The same is true when you apply the same theory for the cosine. This can be done by high school students. Addition of cosine, addition of sine, the same structure. So whether you use usual sine, cosine, sinusoidal function, or exponential function, your circuit in analysis must be the same at the end of the day. As a summary, when we compute something regarding the RLC circuit, it is convenient to describe the system in terms of current. The reference point is current, and resistance is a real number, and Ri becomes a potential that has the real part. And because they are sinusoidal, time derivative or integration over time brings in a change in the phase by half a pi. Forward for the inductive load and backward for the capacitive load. They will bring in the imaginary part of impedance, and this one is in phase. Inductive by this weighting factor, it is forward. Capacitor by this weighting factor by backward, and they are aligned to the imaginary part. And then the amplitude of the whole system is completely determined by this absolute value of the complex number Z, that is R, XR plus I, XL minus XC. And this absolute value is called impedance. So this impedance completely determines the amplitude and energy consumption, for example. For example, we see VL, that are the voltage amplitude for the R, L, and C, they are completely determined by the amplitude for the current and their reactances. It is true whether you attach a small part of among RLC. If you're interested in the voltage difference between the two terminals of this composite system, what you want to do is just consider XR plus I, XL minus XC among this complete form. Keep the R and L contribution. So remove this guy. Then your impedance becomes this. And take the square root data, take the magnitude. The modulus becomes this. And your voltage for this one is. So this is not L, this is R plus L. This is not L, this is R plus C. And this is for C plus L. Okay? Something like that. So in this manner, you can determine the voltage potential difference between the two terminals of a composite system. And the same is true for the calculation of power or an RMS value. As I repeatedly told you, the current I is the reference and whose phase shift is named by phi instead of delta. Delta corresponds to the phase shift for the charge Q. Phi, that is minus phi, is a half of pi minus delta, is the phase shift for the current. Using this, we can determine the power spent by the resistor, and this time dependence can be averaged over time. Specifically, you can take the period to take the time average. The sine squared function has average value 1/2. This 1/2 is included as an amplitude. This is a squared form, so in an amplitude, this one is a square root of 2. 1 over square root of 2 is a square. So 1 over square root of 2 is included into the in the original amplitude. Then you don't worry about the time average. So this factor already assumes your time average. So in that case, the computation becomes very, very trivial. And RMS values can be used for this amplitude and power also. You will find this power has from IR squared, RI squared, we have R dependence in the denominator relative to the impedance. You know, real part and imaginary part. This one was cosine and this one was sine. So because this R over impedance, resistive reactance over impedance determines the rate of power. We call this one as power factor. That's it for today.